Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video today is basically the final homework example from week 16, the final exam preparation assignment. This is the final homework, and you have a couple exam problems, 3 exam problems, and you are done with this course. Run on out of here, enjoy your summer, winter break, whatever it is you're gonna do. So the problem here is I have, those of you who are just watching this outside of my classwork, here's the C++ code, and we're going to go through all of it in detail, of course. But the idea is there's just think of high school. Most people went to high school where there are lockers across, in my case, hundreds and hundreds, if not 1,000 lockers sitting around the school. And let's just say there are 100 of them, and there's 100 students who walk through. And again, the problem is a little contrived, but it's better than trying to explain it in more mathematical terms and just yawning and falling asleep while you do it. So there's 100 lockers, then 100 students. The first student goes and opens all the lockers. The second student goes through and closes every other locker. The third student goes in and toggles every third locker. And at this point, it's a toggle because some of them will be open and some of them will be closed. So it's impossible to know if he's going to be opening or closing, or he or she, as we go through. And so it's toggling all the way on. So the fourth student toggles every fourth locker. The fifth toggles every fifth locker, and so forth and so on, until all 100 students have done their thing. And you go, well, which ones are open after all this? And it's maybe it's surprising, maybe it's not when you run this, but when you follow this through, every locker that is basically a value squared, like 1 squared, 2 squared, 3 squared, 4, 5, 6, 7, 8, 9, and 10, the squared terms are the lockers that are left open, and every other locker is closed. And I'm not going to get into the mathematical reasoning behind all of this. This is a computer science course. This isn't a math course, right? So if you wanted, you could look more into this. There's a very logical reason why this is the way it is. But for our case, so we want to write a program that will do all this hard work and eventually generate this output in assembly language. And to do this, we're going to have to create 4 functions that all work together nicely, and a main function that calls all of this stuff. So I'm going to do this. This is the easy part here, right? Call toggle lockers. Call print open lockers. And call wait message and exit. And oh my God, that would be it. Wouldn't that be great? That would be it. But the toggle lockers function calls student toggling lockers, which that function calls the not operation. And then at the end of the day, print goes through and prints. So one other thing here is, generally speaking, I would, if this was pure C++ and we weren't translating this into assembly language, I would pass along this array of lockers instead of basically creating it as a global. But I made it a little simpler, as much as this is going to be a pain in the butt to get this thing to work, that I made it global, so we're not passing references to pointers and putting pointers on the stack, all sorts of crazy stuff. And so I wanted to make it a little easier. So it's going to go in the data section. This is dword, because it's our int dword. Oops, I'm going to call it locker. No, yeah, lockers. I can spell lockers, dword, and then there's 101 dupe 0. So they're all starting out. There's 101 elements. Remember now, we're going to have to worry about this since every element is dword sized. When I go to access the lockers, like anywhere where you see this, it's going to be lockers I in a high-level programming language, but it's essentially going to be lockers 4 times I, because we have to, in assembly language, figure out which byte in the array am I talking about. And since we're talking about dword for every element is 4 bytes. So basically, I don't think we do anything else than just use I for lockers I, lockers I, lockers I. So at least we're going to simplify that by just every time I see an I, we're just going to move that value over by, we're going to multiply it by 4. And then it'll work for us. So we've got our global, we've got our main, and now we're just ready to fill in the gaps and get going on it. Okay, so a few things I've done here. I've set up the print open lockers procedure here on the assembly language side. I commented this out for the time being. And what I've done over here is I turned that for loop into a while loop. So I moved everything around a little bit. I removed my I value and I turned it into EBP minus 4 just so we can get a feel for every part, every I is this local variable that we're going to use. There are no parameters, but there is going to be the local variable that we're going to use. And so you can see that we can get the value normally here, 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 and here, but this is going to take a little extra work because, again, remember, we're going to take this EBP minus 4 value, multiply it by 4 to get a memory location or get an index, and then get that thing inside of here. So it's going to take an extra step to make this thing work. But we're ready to move on here. So now the ret is fine. There's no parameters, so that's okay. But we're still going to need the push and the move and all that other stuff here on the EBP side because we do have the local variable. And so then I want to make sure I do the pop EBP. And then for the local, I got to subtract off from ESP. I got to subtract off the 4 here, and I got to add it back here. So now the local is taken care of, the parameter is taken care of, and the EBP and everything. So now I just have to go ahead and set this thing up and set it equal to 1. So I got to move into dword pointer EBP minus 4. I got to put a 1 in there. Let me just steal this guy. I hope I can not have to worry about copy pasting too much. But okay, so that takes care of this guy. So now I need my while here. And so what I can do, remember, while requires 2 labels, an unconditional jump, and then the comparison itself. So I'm going to compare EBP, dword pointer EBP minus 4 against 100. How do I get out of the loop? The opposite of less than and equal is greater than. And I'll go to done. I'll do stuff in here. That's where my if statement and everything else is going to go. But then the jump again, and then eventually I'll work my way out with the jump if greater than, right? Because it'll be 101 and beyond. Okay, so that covers how to do the while loop. And so now what are we going to do here? We're going to do this second if statement. And again, this is where things get a little tricky because what I'm going to do here is, let me make sure I do it in the right place here. Okay, so here, now that we have all this going for us, we're going to do it inside of here. I'm going to compare lockers at what I would think is, I would just think it would be EBP minus 4, right? And I compare to 1, and I can do I'm not going to do anything else because this is not right. And so this will compile or assemble. There's nothing technically wrong with it, but it's absolutely wrong because EBP minus 4 is just a memory location. And it's a number, right? If you think about it, EBP minus 4, EBP is some pointer, which is not an index value. It's some number. It's it could be any number at all. Here, let me see. Let's just run it. Let's put a breakpoint on this. And let's see, can I mouse over that? No, I can't. So let me see. Let me add a watch. And I go and I see that the EBP value is 170,000 or 1,703,788. Yeah, that's not right, right? We only have 100 lockers. We don't have 1,000,000 lockers, right? And that's because the EBP value is just a pointer to memory. It's not storing data. So I have to do one extra step to make this work. I have to move, and I'm going to use the EAX register. I'm going to move the value here. And so EAX is still storing a pointer. But what I can do here is, and it dereferences it. So that's what the big difference here. This says, go to this memory location, treat it like a double word, and put the value that is stored there here. This just says, okay, get me the EBP value, subtract 4 from it, and then go to that position in the lockers array. So these are completely different things. So EAX here will store the 1, but here, this will store the 1,000,000 number. And so what I can do here is I can actually say, if I said like EAX now, that's perfectly legitimate. It needs the extra step because the dereference from the memory to get the value to go to that memory address. But remember what I also said earlier was we're using dword for everything, so you can actually go ahead and multiply 4 here. You could also shift, if you really wanted to, you could shift left EAX, 2 to get to the same point. But you can actually go ahead and I know it sounds weird, right? But you can actually go ahead and multiply 4 here times EAX and compare that to 1. And I'm going to call this do nothing. If I can spell, do nothing. Come on, Brad. Okay, so here is my move, here is my compare, and I do nothing if they're not equal. Correct? God bless it. Do nothing. So I say, okay, compare. Go to this memory, get me the value, go to that memory location, compare it to 1. If this is not equal, I don't want to do this, and I'm going to come around and do nothing before I jump back. But if I fall through this, then yes, they are equal, and I'm going to go ahead and move into the EAX register. Whatever's at D word pointer EBP -4, I'm going to call write decimal. I'm going to move into the AL register, the empty space. I'm going to call write character, and then I'm going to fall through. I don't need a jump or anything. I'm just going to fall through, and then the if statement is complete, down to do nothing, and then what I'm going to do here is increment that guy. And when I run this, and first let's make sure it builds before we even think about what will it do. And I run this, and you're like, okay, Brad, it didn't print anything. And the reason it didn't print anything is because we initialized everything to 0 up here, and it's checking against 1s. So let's see, if I set every locker to 1, hopefully it'll print out every number now that I just did this. And I did, and it does. There's my values from 1 to 100. So I know that I've done my function properly, because since every locker is from 1 to 100 is set, and it's printing every one of them, it's doing everything correctly. And so I can set this back to 0 as I go here. And so now with this function set up, and it's a void function here in C++, my final step before I move on to anything else is to go, what registers were blown out and need to be put back? Because as you can tell, there's 4 functions working together. Modifying registers is something I do not want to tinker with and accidentally blow out and have somebody lose track of things and have to debug this later on. And so EBP and ESP are taken care of, and what's left here is EAX, AL, and AL is a part of EAX. So I do have to go here and put a push EAX here, make sure everything's in reverse order, right? And a pop EAX here. Oops, I don't know why that's there. Okay, and now you'll get the same results. Nothing will change on the output side, but now I know that everything's going to work on this end. And again, if you like doing things this way, I can call dump regs before the function, dump regs after, and just make sure that the 6 major components here, EAX, EBX, ECX, EDX, ESI, EDI, are not modified before and after, and they're not. All the work is done, right? Even if I go back and do a dup1, you'll see that the registers are not modified, or at least it appears like they have not been modified, but I still get all the printouts as I was expecting. And again, remember, EBP and ESP, like I think EBP you could presume, especially if you did everything right with the pushes and the pops, will be put back. But as you can see, the ESP doesn't have to always be back to where it was. It could be a different value because you don't necessarily control the stack. Right? I mean, you can control, you're kind of manually playing with the runtime stack. You're kind of playing computer god here with making sure everything works, but with great power, oh my God, he's going to say it, with great power comes great responsibility when it comes to making sure that for every push and every move and every add and every whatever, that the push has a pop, the sub has an add, the push has a pop, the ret, if I pushed parameters down here, that would ret whatever number. I'd put a number here to indicate that I was done with that stuff too. So I'm pretty confident, and we'll see when we open this up later, but I'm very confident here that the print open lockers function is complete, and I'm ready to move on to the next thing. So the next function is the toggle lockers function, and that's going to basically start calling up the chain to all sorts of other things. So toggle lockers will start out, it doesn't take any parameters. Okay, so that's just the basics just to kind of get it going. And let's take a look at toggle lockers. Okay, so now, oh boy, so this function's calling another function, and this is a for loop. So let me just start playing with it here. While, up, and move this guy out, just like we did before. A lot of repetition with these loops. Like, oh, repetition. Well, that's what a computer does, right? So I'll just down here, plus plus I. And so we're looking at something like this when it comes to this function with a semicolon there. Let me run this function again just to make sure with all the changes I've been doing that I still get the correct results, and I do. Okay, and again, like I did before, I'm going to replace every I here. Since I'm localing up, every I becomes EBP minus 4. All right, so now let's take a look at this and go, okay, and now the same thing as before. Because I have a local, I need to do my push EBP. I need to do my move EBP, ESP. I need to do my pop EBP, and there's no parameters passed in. So once again, I don't need to worry about the ret. And just like before, I need to set my EBP minus. I need to do my subtraction for my local. If I said that incorrectly, otherwise I apologize. I need to subtract off from ESP my 4 so I can add it back here. And now we have everything ready to go, and I can move into dword pointer EBP minus 4. I can move the 1 again. Steal this because we're going to borrow this again. And now, again, I have a while loop, so just repetition, right? I have an again, I have a done, I have an unconditional jump, to unconditional jump to again, and now here is my conditional. I'm going to compare, like I did before, this guy, EBP minus 4 to 100. I'm going to get out if it's greater, just like I did before also, to done. And that handles my while loop. Okay, so now what's left here is these 2 lines of code. Make this a little small end there so you get that. And so now there covers my while loop. 5 lines of code, 5 things going on here. Two labels and 3 lines of code to get this work. And so now what can I do here? I need to push onto the stack to call a different function. Whatever's stored at this, get me the value. I need to call the student. I haven't created it yet, though, of course. Toggling lockers. And then everything else will be taken care of. And when I get back, I want to increment that. There's no way to test this right now, obviously, right? Because this function isn't been defined or created or even written yet. And then as you'll see here, that function is going to call another function to do the work of, basically toggling all the lockers. And so right now, what else is going on here? I'm pretty confident it's going to work because I'm crossing my fingers and I'm just praying to the assembler gods here. But what I'm saying, if I go back right now before I go into anything else and I go, okay, I have not modified any registers at all in this function, right? I'm using memory, I'm pushing memory, I'm incrementing memory. There's nothing here that is a local variable. I'm not dividing, I'm not multiplying, I'm not looping with a loop instruction. I'm not doing anything out of the ordinary here that would be indirectly changed. So I'm almost 100% confident that, since through repetition and just getting the feel of it, that I've done everything correctly. I've done my translation correctly. So now, moving on to student toggling lockers. Here we go. And we're basically doing almost the same exact thing, just a little different here. The code, oh my goodness, look at how things are. This for loop is a little different than we did before. Let me small this one more time now. And let's look at turning this into a while loop. Stealing this guy. While this is happening, go ahead and do stuff. Steal this guy, bring it down. Okay, so there we go. So now this is what I want to accomplish on this end. And remembering that it's easy on the high level side, we're just going to have to multiply this by 4 because, again, we're dealing with double word elements. So we're going to have to multiply by 4 to get each byte boundary in my array. But we have ourselves, and instead of just setting everything up appropriately, now we have a parameter that's getting passed. So this is EBP plus 8. So anytime you see an X here, this is going to be EBP plus 8. And then this I is going to be like before, it's the EBP minus 4. So kind of the same, kind of different here, right? Oh my goodness. And I will fix this up so you can see everything here. Let's see. One more. There we go. And let's get this all on. Let's get this so you don't have to look at all the extraneous stuff here in the moment. So what we're going to try to do is generate this code without defining the not operation. So let's go to that. Let's set that up right now. Okay, so here is my skeleton outline over here on this end. And remember, we did this right. I pushed the value on the stack and called. So I'm going to need a ret4 here. And since I have a local and a parameter, it doesn't matter that they're both, it's one or the other, requires me to push EBP, move ESP into EBP, and then do the pop back before I return. And since I have the local, I'm going to do the same thing I've done before. I'm going to subtract off from ESP, 4, and then add here. So all that hard work, and now I can finally get to business. And so now, let's see, this is equal to this. So remember, you can't do anything in assembly language or on the CPU. I can't do two pieces of memory at the same time. So I'm going to have to go ahead and, before I do anything else, I'm going to use a middleman, use EAX as my middleman, and do move, let's see, dword pointer, whatever's at EBP plus 8. Move that in. And then I'm going to move that into, oops, not that, not that. I'm going to move that into EBP minus, oh my goodness, EBP minus 4. Whatever's in EAX, right? So this goes to here and this goes to there, so it's the same as this equals that. Okay, so we got that line going here. So while loop, it's like we've never done this before, right? So I have my again, I have my done, I have my unconditional jump back, and I have my conditional compare dword pointer EBP minus 4 to 100, as we've done jump if greater than to done. Okay, there we got that going for us. And now we can do everything else inside of here. And so this is the hard one, right? Oh my goodness, there's a lot going on here, right? So what are we going to need to do? We need to get this location, right? Lockers, or we want to pass along, oh my goodness, a value. We're trying to get a 1 or a 0 here, right? Because this is taking an int. It's not taking a memory location. It's just taking a 1 or a 0, and then it returns back its opposite. Turns a false into a true and a true into false. You know, basically the not operation with Booleans. And so this is what's important to me right here, is lockers at this value. And remember from earlier, I can't just go ahead and, I think this one down here, right? It's 2 lines of code to make this thing work. See where I can find it here. Where I have to, come on, where are you? Where are you here? Oops, I guess I can bring this up. Yeah, here we, nope. Oh no, where are we? I know I did it. Pair to 1. But anyway, the whole point is I have to do two lines of code to get me to this position to where I can push it onto the stack. So I can go ahead and, now that I've ruined everything, there we go. So I can JGF done. And now what I can say here, move into EAX, the dword pointer at EBP minus 8, or minus 4. Where did it go? Maybe it's up here. No? Up here? Yeah, it's probably up here. Yeah, see how I had to take the value, move it into EAX so that I could get the actual value, not the memory location, so that I can access the array. Yeah, I found it. What do you know? Anyway, so, okay, so go get me EBP minus 4, move it in there, and then what I can do is I can push lockers. Now this is, lockers of 4 times EAX. Because I can, now that I have the value, I want to multiply that by 4 so I can tell it what index inside of lockers to go. And I need to do that since assembly language uses bytes and high-level languages uses data types as it knows how many bytes it is. Let me see what happens if I build this. I wish it would just rebuild succeeded. Oh, okay. I hate when it doesn't print anything. Goes. And so if you want, I guess you could use D-word pointer if you wanted to, but it knows that lockers is a D-word array. So it knows that when I say get me an element, it knows it'll be a D-word sized element, and then it'll push that onto the stack. You don't always have to put the D-word pointer in front, but if it makes you feel any better, I guess you get to the same spot. But sometimes, like I don't need it here either, because it knows that it's going to go to this memory location and get me a double word because the EAX is the context. I like to be superfluous. I like to be redundant because it just makes life a little easier. Even though it's a little more code, I don't have to think what I'm doing when I'm doing it. So all of this now, I've pushed this value onto the stack. Right? That's what I wanted to push, was this onto the stack. So now I can call not operation. Okay. And now, again, we haven't written that yet, so all of this is just in flux here at the moment. All these moving parts trying to work together. But when I call this function, the EAX register is going to hold the value that I want to put at this memory location. So what I can do here is come back one more time, and I go, okay, so when I do this, EAX will hold right-hand side of this whole thing, right? So now, just coming back, I'm just going to do this step for step like I did before. I'm going to say, okay, get me EBP -4, treat it like a double word, put it into the EAX register, move it over 4, but instead of pushing and doing all this stuff, I'm going to move... Uh-oh, I can't... see, this is where things get a little tricky. EAX is holding a value. I can't use EAX anymore, because then I will blow out the result. So I'm storing it somewhere else. And so now I'm changing this up to say, okay, get me the value of EBP -4, store it in EBX, go 4 times over, and now put EAX in there. Oh my goodness, right? Let's make sure this builds. That was a lot. Uh-oh. And again, the only thing wrong right now is that I don't have a not operation. So let me just prove that it's going to work for me by putting this thing in. Oops. That everything else will build at least. And again, I'm not 100% certain. I feel good about things. A lot of times you can get a feel for if you're doing things right or not. I have a feeling I'm doing okay. And then my last line of code here before the jump back is this guy, right? So I need to move basically the same thing as this one, right? Because it's, but this is a plus equals and not just an equals. So I can borrow this, pop it in, and just change the move into an add, right? This is what I've just done. Get me EBP +8, store it in a register, and then add it to what's at -4. Oh my goodness, right? So now the question is, before I move on, and things are getting more and more shaky because there's less solid ground here, there's no way to test this necessarily right now. But now the final step here is, what registers have I modified? Again, this is another void function. So anything I modified inside of here needs to be put back to normal. And I did use EAX and I did use EBX. So I do need to push those onto the stack and pop them back in reverse order. Make sure I do it in everything has to be in exact order so everything goes back to the right places. EBX first, then EAX, then the addition, then the pop of EBP, then the ret with 4. All right, there's a lot going on, right? How many of this, like half the code is just pushes and pops, and the other half is the actual code that we're trying to accomplish. Let me try one more time, make sure this builds. Rebuild all succeeded, good. So, okay, so our final step here before we can finally test everything, because what happens if I run this? I don't even know if it'll crash. Right now it crashes because we haven't necessarily done everything properly. We'll see. Maybe I broke something, maybe I didn't. Maybe you're already screaming at me, what's wrong with you, Brad? Which is, just normal life, being a married man. No, just kidding. But let's see what happens when I fix up the not operation, and then we can go back and kind of, tinker with things and see if what's broken, if anything, and it looks like something might be broken. Okay, so coming back here, this is a function. This is basically just a fancy if statement. If x is 0, return 1. If x is not 0, return 0. That's all, because it's just changing a 0 into a 1 or a 1 into a 0. Okay, so where did I start this thing off here? Okay, so I have one parameter, so I'm going to ret 4. It's just a simple check. There's no local variables here, but there is the parameter. So I need to do the push EBP. I need to do the move EBP ESP, and I need to do the pop EBP. All right, push, pop, move, ret 4. No local, so we're good here. So I can compare. This x is EBP plus 8, right? So I can just to keep consistent with what I've been doing. Compare EBP plus 8. Oops, sorry. D word pointer EBP plus 8. Compare that to 0, and say, okay, if not equal, then jump to is 1. Otherwise, we'll go down here and say is 0. Because that means that if it falls through here, it means it's equal, that these two are equal. It means that this value here is a 0, and I'm just going to move a 1 into here. I want to return a 1, and then do an unconditional jump to done. Otherwise, if it's a 1, I'm going to move it to 0, and then just fall through and be done. I don't need to jump to done because I'm at done. So now the big question is, first thing is, okay, so I succeeded on my build. So the next thing is, what happens when I run my entire program, all 99 lines of code and all? Oh, I do run, and I get weird stuff, but that's because I started with 1s. Let me see what happens if I run it with 0s. Holy frickin' criminy. Yeah, I got it to work. Nothing's wrong. I got it to work. And just to prove it here, what would happen if I put it up to 1,000? Every power of 2 should print out. Oh, but I only did this to 100. I'm not going back in here. Should I go back in here and change every 100 to? No, I'm not going to do it. That's why we don't like using magic numbers. So and magic number is the 100 or the 101 here, because, well, what did I do? I wish I could just change this one value and my whole program would run properly, right? It would know to go up to 10,000. But to change that, I have to go in, and this is where the bugs come in, obviously, right? Because I'm like, oh, I just changed one number, and it goes, nope. But what if I was just expecting it to work? Or what if I forgot some key detail? Like in this case, how many, I have to replace it here, I have to replace it here, I have to replace it here, 3 places. And what if I forget? Or what if I have multiple things that are 100s, like multiple variables that are 100s, and I only want to change some 100s, but not all of them, and so forth and so on. And so, this is why it's not a great idea just to use a hard-coded number. But I'm not going to necessarily worry about it. But well, I'm just going to do this real quick, since I know I need to change it in 3 places here for right now, just to see if I expand this thing out, that every power of 2 prints out. And here you go. Every power of 2 up to and including 10,000 will print out, because that is the algorithm, or that is the result of this. So 121, 11 squared, 12, 13, 14, 15, 6, 7, 8, 9, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 35, 40. You can see it on here. Every square of every value from 1 to 100 prints out. So yes, my code is working. One thing I didn't do here is to go through, I did the EAX thing here, the NOT operation. I do not have to tinker with anything because the EAX register can be modified. EBP and ESP are already taken care of and nothing else is modified. I took care of EAX and EBX here. Yep, so, and there's nothing that needs to be modified here. And yep. So I have done everything I was expecting to do, and it all works. So let me go through the code one last time here so you got an explanation before I call it a day. And if you don't want to listen to me, and who knows how many of you are listening to me, and you can follow through or not. Stop the video. So I'm going to call this toggle lockers function, which goes ahead and just says for every student, for every student from 1 to 100, go ahead and do the not operation. But anyway, you can kind of see what's going on here. So this toggle lockers function goes ahead and it says for every locker, first lockers, every second locker, every third locker, every fourth locker, and so forth and so on, go ahead and toggle down here. This is toggle, student toggle. What's the difference here? So this is why I was confused and talking weird 15 minutes into this, and I'm not stopping now. Get the mistake, you got to deal with it. Okay, so every first locker, go ahead. Every second locker, go ahead. Every third locker, go ahead. And then here is where you actually go through and modify the lockers. Modify the first, the second, the third, the fourth. And this not operation just goes ahead and just negates the value stored in each individual array. So let me see. There's no way I can get this thing. There's no way I can get this thing onto 1 without it being completely invisible. There you go. I can nope, still need one more. There you go. Can you see that? Of course you can't. So let me bring it in a little bit here. So let's see. Can I get this all onto? Let me get this all onto 1. There we go. So there is the print open lockers procedure in all of its glory. Let me get rid of the 100. Bring this back down. So there's print open lockers in all of its glory, and it prints everything from 1 to 100 and just prints the open ones. Here is the not operation. So it turns the 1s into 0s and the 0s into 1s. Here is, oops, we got it? Nope. Do we have it? There we go. There is our student toggling lockers function that does all the work to go ahead and do the hard work. Here is the toggle lockers function that goes ahead and says, why don't you go ahead for every first locker, every second locker, every third, and so forth and so on. Let me bring it back one more time. There it is. Oops. There we go. And then for the main, this thing gets everything put into motion, and then the end results get printed out. Let me run this one more time to make sure I replaced all those 10,000s with 100s, which I did. And we're all good to go. So this was definitely an involved problem. If you're able to do this in any amount of time, I would suppose, like, you're ready for the final exam. If you can get this thing working, put together and working and working properly with all the bells and whistles and all the pushes and pops and all the moves and everything here, you're ready to get your A, 250 out of 250 points. Move on and go on to bigger and better things. So, as always, thanks for sticking with me on this one. Big, long problem. If I have any mistakes here, which doesn't look like I do, but if it's very possible I still do, please email me at swardb@cod.edu or comment below here on YouTube. I'll get back to you as soon as I can, answer those concerns and questions. Anyway, have a great day, everybody. Good luck on your finals. Send me any questions you have. Talk to you then. And have a great day.